Hi again, everyone. Thank you for joining us today for this webinar. We can start it now. The topic of today's webinar is going to be undrained analysis and undrained materials. I am Alireza Azami. I'm Director of Business and Research at Rocscience. And today for this webinar, my friend, Dr. Sina Moallemi, who is the project manager of RS2, will be helping me by moderating this webinar and the question sessions. Okay, so about Rocscience, you might probably know us. We are the world leader in developing innovative 2D and 3D software for civil, mining, and geotechnical engineers. We are dedicated to delivering industry-leading software programs, exceptional customer service, and unparalleled technical expertise that engineers can rely on. And from the team of 4 at 25 years ago at University of Toronto, we have grown to a team of 80 with 4 offices and many representatives across the globe. So in terms of offices, the headquarters is in Toronto. We have another office in Vancouver. We have offices in South America, Africa, and Australia. And all around the globe, we have representatives that they represent Rocscience. What we do, we develop tools, software tools that is inspired by users, which will be you. And we have 19 programs at the moment. They can be applied to different applications in soil and rock. We have them 2D, 3D, and different combinations. Your input will drive the development of all these softwares and the features. So we would appreciate your feedback anytime, any moment, any way that you can get them to us. And we try to include innovative solutions to our softwares. We are in contact with most of our users in person and through many webinars, courses, and other connections that we have around the globe. And we are also in touch with universities to keep our tools at the top of the technical expertise. Now, these are all the tools that we have at the moment, 19. 2 more are in development. We'll be presenting those as well, hopefully next year. And what we have in Rocscience, we have the software ecosystem that we have. Our softwares are tools they can talk to each other. So for example, if you are making a model for slope stability in slide 2, you can just drag and drop it in RS2 and run a finite element analysis in it. If you are calibrating your material properties in RS data, you can import it, those properties that are calibrated, you can import it in other tools and run more meaningful analysis using them. Now, for today, I will be using RS data and RS2. And the functionalities that I will introduce are mostly available in RS3 as well. So the focus will be mostly RS2, and we are doing mostly finite element analysis here. For undrained analysis and undrained material, the key features that we have in webinar include hydromechanical coupling using biotheory. We will be talking about undrained analysis, which is a special case of that coupled formulation. We will be talking undrained versus drained material in RS2. There are 3 different modeling methods that we have here. I will address the material properties definition in all of them. And we have verification and case studies that I will present along the way. We will start with the formulation first, the coupled formulation. So in RS2 and RS3, what we have for hydromechanical coupling, we have fully coupled consolidation analysis, which is based on the coupled solid fluid analysis based on biotheory, that UP formulation that we have. I will present the formulation as well. On top of that, what we have uncoupled consolidation analysis, which is a special kind of consolidation analysis that we can run in these tools, which is based on the methodology that we have actually in our other tool, Settle3, which consists of 3 steps of analysis in each of these stages that we have in RS2. First one would be calculation of excess pore pressure that is caused by the loading that is applied to the system. We are using that Skempton B coefficient for that. The second step is to the pore water pressure dissipation and distribution in the domain. We are calculating that with a transient groundwater analysis. And in the third step, we are running the solid analysis, considering the loading and also the distribution of pore pressure that we calculate in the second step. Now, doing all these analysis, what we have different drainage conditions that we can consider for the simulation. It could be drained, undrained, fully drained. I will explain these along the webinar. We have an extensive library of constitutive model that allows for linear, nonlinear material behavior analysis. And we have options for permeability function and soil water characteristic curve that you can apply in unsaturated zone. Now, in terms of general consolidation equation, this is that the UP formulation, Biot formulation that we have. So what we have here, we have the stiffness matrix, coupling matrix, compressibility matrix, permeability matrix, and we have time. The way to solve it, it's a coupled analysis. You can see that all these terms are present here, and you have displacement, pore water pressure at the step n+1. You can calculate it, and when you solve this system of equation. And this is fully coupled, so you have to solve both for displacement and pore water pressure at the same time. In terms of solving this system of equation, is quite expensive in terms of computation. Now we have simpler version of it. If you would like to only deal with undrained analysis or drain analysis. So modification of that equation for undrained analysis, what we can do, we can set permeability matrix to 0 and time is going to be 0. Then we end up with this smaller system of equations. At least the form is condensed. It still is coupled because you have U displacement, pore water pressure here, and all these terms are present here. So still you are solving a system of coupled equation. For drain case, which is you can say it's a one-way coupled. So you can solve your for pore water pressure from this equation, and having the pore water pressure as a solution for the first round of analysis, you can solve for the solid as well. So in this one, you have the stiffness matrix, coupling matrix, and permeability matrix. So as a special case of that UP formulation that we have, you can have undrained and fully drained condition. How we define this in RS2? So in RS2, in the solver option, we can select the consolidation option to be coupled or uncoupled. I will focus on coupled mostly here. And within the stages that we are running the analysis, we have options for each stage. That the stage could be drained, undrained, or fully drained. If it's drained, we are using that fully coupled formulation, that UP formulation that we have. If it's undrained, we are running that modified version of the undrained case. If it's fully drained, basically we are going for that fully drained condition that the system of equation is not coupled anymore. So we solve for the groundwater, then we solve for the solid. So this is how we can set up different configuration of the analysis in RS2. Now, if you are interested in undrained analysis in RS2, these are the combination that you can use. So you can have consolidation bio, you can go for drain, meaning that you are using that bio formulation completely. But if you have small time steps, you will not have enough time for the dissipation of excess pore water pressure in the system, meaning that, okay, you're basically running an undrained analysis. Or you can go for the simpler version, slightly simpler. You can go for coupled bio formulation and use that undrained analysis. So within all those stages that we have in RS2, you turn them to undrained. We have the same configuration when you have that consolidation set to uncoupled. Now, just to show you how this works, I will demonstrate all these different type of analysis on this undrained foundation problem. The problem that we are looking at here is strip footing. We have undrained conditions. We are ignoring the unit weight and gravitational forces. The material is fully saturated. Initial field of stress and pore pressure, these are all set to 0. All these assumptions that I have here, these are so that I can have the analytical solution for the bearing capacity. And I show you that all these analysis type that I'm doing, all these material type that I'm using, they are working properly and I have the correct answer for this bearing capacity problem. So these are the properties of the material, elastic modulus persistence ratio. These are the effective terms. We have the strength of the material defined by cohesion and friction angle, 30 degrees, 1 kPa cohesion. And if we are looking at this material, starting from initial state of 0, and assuming that failure criteria of more Coulomb, the path to failure under undrained condition for this one will be, okay, we don't have no volumetric strain. We have, in that case, d epsilon 1 equal to minus d epsilon 3, so no volume change. And because it's a plane strain condition, d epsilon 2 is going to be 0. So if this thing is going to fail, at failure, we will have that d sigma 1 equal to minus d sigma 3. And if I put these two values in this equation, I will get these two equal to c prime cosine 3 prime, 0.866 kPa. If I'm looking at it in normal stress versus shear stress graph, the orange line is the original material properties that I have. This more circle is representing the failure that I predicted here. And if I'm going to represent this material as undrained behavior, undrained shear strength of it is going to be this value at the top, which is 0.866. So SU is going to be 0.866 for this material in undrained scenario. Now, if I'm looking at bearing capacity for this undrained scenario that I have here, the bearing capacity from this equation that we have, Q is equal to NC multiplied by CU that I have here is 0.866. It is going to give me the bearing capacity for this one, 4.45 kPa. So to simulate this one and as a verification, show that this is going to be the maximum load that this foundation is going to carry in undrained condition, I'm applying this load at the top. This is a 1 meter width of the footing. The load that is applied at the top is 4.5, slightly bigger than this one, and I'm applying it through 14 stages. So what I'm expecting to see when I'm running the analysis is that at least at the very final stage, I will have the failure and I have the maximum load. Now, let's run the simulation to see if those analysis type that I mentioned, they can actually capture that undrained behavior that I expect from this with that maximum load. So first case that I'm running is going to be consolidation, coupled consolidation, but the load that I'm applying to the system, it has a rapid rate. Time steps that I'm applying the load here, they are very small. The material that is defined here, it is all defined in terms of effective stiffness parameters and effective stiffnesses. And let me show you actually the model. So that is the RS2 model. Let me go to one of the stages in the middle. So the load is increasing step by step. The material properties are given here in that table. So all are defined in terms of effective parameters. And the setup that I have in the project setting, I have the solver option. This is coupled. And we have the stages. These are all drained, meaning that, okay, I'm running that coupled formulation and they all have time. Okay, let's look at the results for this one. Let me open it in the interpret. I'm getting a warning here. Let's look at the log file. You will look at it. And these are the results that I'm seeing. You're looking at the vertical displacement. And also you can look at maybe seepage excess for water pressure in the domain. Looking at the log file, let's go to the very end. What I have at the very final stage, I have non-convergency, meaning that, okay, the load that is applied to the system is not is passing the capacity. And the one before that, actually, you can see that I had lots of iteration to converge. Before that, I have way less number of iteration. From the graph, you can also see we are looking at load versus displacement. You can see that it is flattening at the peak, which is close to 4.5. The pore pressure that I'm showing you is half a meter underneath the footing at the center. So you can see that also this one is showing you that generation of excess pore water pressure in the system. This was the case that we did fully coupled analysis. We had time, but the time was short so that we didn't have enough time for dissipation of excess pore water pressure. We mimicked that undrained condition. The next case that I'm going to present is undrained analysis, coupled consolidation. Okay, for this one, again, gradually we are increasing the load. Project setting says coupled stages, they are all undrained. Now let's look at the graph for this one. The green line, this is that undrained analysis, coupled consolidation. So we don't have any time here, but as you see again, we are predicting that maximum load correctly, and the load displacement is very similar to what we had here. Similar behavior we saw for pore water pressure. The other option would be when we are looking at uncoupled consolidation. So the coupled that in the project setting, you just set that consolidation formulation to uncoupled. Again, as you see here, all of these, they are matching the same pattern for low displacement and also development of pore water pressure. In all of them that I showed you so far, the 3 before, we were using effective strength characteristics, C prime and phi prime. If in any case I want to use SU in terms of strength only, you can see that again, the predicted behavior is very similar to what we had before. But my main focus here was the previous three graphs, so coupled and coupled formulation, undrained condition, or rapid rate of load, but using effective parameters in terms of stiffnesses and also strength of the material. So that would be for the case of undrained analysis. Now let's look at undrained material. Undrained material would be a simpler way to consider undrained behavior for materials. In this case, when this option is activated in RS2 through hydraulic properties dialog for each material, you can activate it. The undrained effective stress analysis combined with effective strength parameters C prime and phi prime, and with the calculation of pore water pressure, in essence, we can actually capture that undrained shear strength of the material. So this is the effective stress calculation that we have in this formulation. Very similar to what we have in general, but we have the alpha bio and Biot coefficient, and we have that effective degree of saturation. So the formulation that we have here is actually developed to capture the saturation, the effective degree of saturation as well. Just to show you what this does, let me go to this one. So if we are looking at a modified camp clay, for example, material, what we are expecting to see in triaxial test simulation, if it's drained, for example, in PQ space, effective stresses, you have a straight line 1 to 3 slope going up. If we are looking at undrained, let me animate the undrained behavior. So the undrained behavior, if we have your pre-consolidation, OCR, the stress path is going to go straight up, touching the yield surface, then you have generation of excess pore water pressure in the system. Now, this was RS data. Let me close this. What is happening if I'm looking at any material in RS2? So the simulation that I'm showing you here is an RS2 example. We are running triaxial test on this material. Let me zoom in to see what kind of material we are dealing with. It's a hardening soil material. The material is considered drained. I'm running triaxial test on it. Let's look at the results. Okay. Let me close this one, open it fresh because we are working on this one. Open a new interpret for this one. So this is the stress path that I see for this material in terms of when you have drained conditions. So effective one misses or Q, this is effective mean stress. So you have a straight line going up. You have compaction, then dilation. There is no pore water pressure in the system. Now, if I go to the model and just turn the material to undrained, in the hydraulic properties, I can say this one, make it undrained. That's the only change that I do. I'll say, okay. You can see that, okay, this changed to undrained. I'm just going to save it and go to my interpret. The interpret says, okay, I lost the result. The file has been changed. I'm going to say run the compute. It is running the compute engine. It is done. And the results are loading now. Now we are looking at undrained behavior for this material. This is effective stress path. So you have generation of excess pore water pressure, positive, then negative going up. This is pore water pressure generation, positive going down, negative. And there is a slight volumetric behavior change. And it's very little, but that's because the material now is considered undrained as near, and it's nearly incompressible. What are the formulation behind it? So the general finite element equation that we have for this case, for undrained material, we are using an equivalent stiffness matrix to account for this undrained material. What we have here, KEQ equivalent multiplied by displacement only equal to the out of balance forces. And this is divided by effective part and the part that is coming from the undrained behavior. And these are how they are defined. So that to account for that undrained material behavior, we have all these matrices to be calculated and considered in the simulation. One of the things that we have in RS2, which is an advantage that we have, is the formation of this E matrix here. And the way that we have formulated this one is going to help with the stability of the system of equation that we are solving, because in most cases that what we have in undrained condition is the incompressibility of the element and material. So this term can actually handle that, and we can have Kw, the bulk modulus of water, defined as the exact value that it should be. And what we have for unsaturated cases for now is we can have negative pore water pressure from the project setting, and based on that Kf value, which is here, is going to adjust the effect that we are seeing from the pore water pressure in the system. We have more development coming to consider more options in the unsaturated condition as well. Now, if you want to relate those equations to Skempton B parameters, and between bio alpha and bulk modulus of the solid skeleton, and also water, this is how you can calculate that B Skempton. So this is your bio coefficient. This is bulk modulus of the skeleton, solid skeleton. This is bulk modulus of the solid particles, and this is the bulk modulus of the water. So we are using the actual value for it. If in any case you want that B parameter to be something that is not as close to one that this equation is going to give you, you can actually manipulate that Kw if you are interested. Okay, now let's go back to the same undrained foundation that we had. All those undrained analysis type, they gave us the correct results. Let's look at undrained material. There are three cases that I will address here. Case A, B, and C, as you might know them. Case C will be the case that we are assuming that the material, the undrained material, the whole mixture is going to be one entity, and we are dealing in terms of total stresses with this material. In that case, we are defining stiffness characteristic and strength characteristic all in terms of undrained cases, assuming that, so the shear modulus is going to be the same for undrained and drained cases. We can calculate that one. This is the effective stiffness. And for undrained case, Poisson's ratio is going to be close to 0.5. Based on that, elastic modulus for undrained case is going to be 12,500 comparing to 10,000 for drain. Now, looking at the results, again, the load displacement is exactly the same as before, but this one, because we are dealing with the total stress condition, we don't have any generation of excess pore water pressure. This is all included in the type of the total analysis that we are considering for the material. Now, we have other options. You can call it undrained material B. In this case, we are setting the material behavior to undrained. We are using the stiffness characteristic for drained effective stress, but the strength characteristics are defined with SU. Let me just show you the material properties for this one. This is case B. So what we are running again, consolidation option is off. There is no consolidation happening here. There's no time, no nothing. The material, if I go to hydraulic properties, this one is undrained. And what we are defining, the stiffnesses are going to be in terms of effective, but the strength of the material, the peak cohesion, you can see that I'm using that SU value for it. So this is undrained B case that we are dealing with. Going back to presentation, the yellow line is the behavior that they're predicting for that undrained foundation. So again, we are predicting all load displacement and also generation of excess pore water pressure exactly as we had for the analysis, for the undrained analysis. Last case, we have undrained material A. Material behavior is defined to be undrained. The stiffness and strength characteristic, these are all defined in terms of effective stresses. So E and nu and C prime and phi prime. Again, when you're looking at it, load displacement exactly as predicted before, pore pressure displacement exactly as what we had with all these different methods that we have. The only method that is not giving that pore pressure to us is that undrained C material, which we didn't even consider the pore water pressure in that one. Now, I'm gonna stop on this graph here. It's there's a lot of information in this one. If you have any question on it, you can actually type in your question. box and we can try to address it. And Sina, if you have any question for me to address.
Sure. Thank you so much, Alireza, for the great presentation. Maybe the first question is kind of a summary of what you presented for us. What is the difference between setting material undrained from the property dialog and from the stage tab in the project setting? When should I use either of them? Okay.
In terms of, let's consider undrained analysis compared to one of those, maybe undrained B. In terms of formulation that we are solving, when we are going for undrained analysis, the size of the matrices are different comparing to the size of the matrices that we are solving in undrained material case. In terms of what matrices are involved, basically they are equivalent in terms of equation, but what we solve at the end of it is going to be different size of matrices. In terms of stability, when we are dealing with undrained material, the solution is more stable. It can converge to the results better. And undrained material has more flexibility. So you can define which material is going to be undrained, which one is going to be drained. I will have it in the next example coming up. But when you're defining an undrained analysis, everything is going to be undrained. So if I'm going to pick one of them, because undrained materials, they have more flexibility, I will go with undrained material, and probably my pick would be A or B.
Thank you so much. The second question is how to deal with incompressible elements.
Okay, so what we have within all this formulation, we have so numerical instability, numerical issues with incompressible elements. The way that is handled in RS2 and RS3, within those matrices that we have, for example, that E matrix that we have, we are using a special case of shape function and a special case of integration that we have within the element, inside the element, so that we can overcome these kind of issues. And since we have those, we can actually have that KW equal to the actual value that we have. And even when you have stiff material combined with a stiff, the water is already stiff, we have those scenarios, we are still able to handle those kind of scenarios. I know some other tools, they are not actually using KW equal value to the actual value that it should be. In RS2 and RS3, we can have that.
I see. Excellent. The other question is, in the strip footing example that you just showed, why you were using the drain properties like for C and 5 for undrained analysis?
Okay, so what I wanted to do in that one, I wanted to use everything in terms of effective strength characteristic, effective stiffness also. I wanted the analysis itself to handle the undrained behavior that is considered there. So if I wanted to consider in terms of strengths, if I wanted to consider strengths to be undrained, I showed you those cases. Those are okay as well, but this load displacement that we are seeing here from undrained analysis, I don't need to adjust the stiffness. So the adjustment that I did for a stiffness of, for example, C, I don't need to do it to here. So the undrained nature of the problem is going to be handled by the analysis type.
Okay, and maybe, yeah.
What I would like actually in this scenario in terms of analysis, this is my favorite. Historically, I have been working with the UP formulation. It's the whole major thing at the top, and the other ones are derivative of that. When you are doing that consolidation analysis, usually you have everything in terms of effective defined there, and everything else, if it is undrained or whatever happens, is defined by the permeability or what time that you have for the analysis. It's going to be handled in those terms.
Okay. Okay, so maybe the last question for this section, again from the same person, should we have dilation angle values for undrained analysis?
Okay, so the example that I showed you for that the hardening soil, this one. So this one, you can see that, okay, properties, define material, go to strengths, I have dilation angle. So if you have dilation angle for the material, you know what it is, yes, you can use it. But in most cases that I will show here, I was going to simulate behavior that we see from clay materials. So even the material that the example that I will present later is going to be clay material. So in all of them, I'm using dilation angle equal to 0. If you have dilation angle, as you saw here, this formulation that we have for undrained, it is able to handle that. There's no problem there. But when you have dilation for undrained material, then you have the generation of negative excess pore water pressure, and the material can handle higher level of shear stress. So it's just the material properties. Yeah.
Okay, I'm going to pass it to you, and we'll ask you the rest of the question at the end of the webinar.
Thank you very much, Sina. Okay, so now we are done with the verification case. Let's look at a couple of examples that I have here. So the first one is we are looking again undrained material. The case that we are looking at is Taipei National Enterprise Center excavation, which is a brace excavation. So this one is a 18-story structure with 5 basement levels. This was constructed in 1991. And the excavation for its site completed within the top-down construction method across 7 stages, which took place over the span of approximately 300 days. The results and material property that I will present here is from the references that I have here, and also this second one here. And the simulation that we run here in RS2, it has 9 stages, so 7 stages for excavation and 2 stages for initial stage and also installation of the wall. And the rest of them would be excavation and installation of the support coming in. Looking at the geometry and the mesh on the right side, we have different layers of the material. We have different support elements. These are those slabs that I have simulated them with the spring element. And we have different materials. The mesh is refined around the wall. And a bunch of the materials that we have here, these are sandy material. So the assumption is that the permeability for these materials is high enough, so at no case they're going to be defined as undrained material. So these sand material parameters, these are defined in terms of effective stiffness and also effective strength characteristic, and their behavior is going to be set to drain in the simulations. So behavior drain, you have friction angle and cohesion for them, and these are all effective and drain conditions for these sandy material. But for clay materials, I'm using both those 3 options that I gave you, A, B, and C. For the case that we have clay parameters, undrained material C, we will be using undrained stiffness characteristic and undrained strength characteristic, SU. So these are the parameters that I'm using here. And since we are dealing with it as a total stress kind of a scenario, the material behavior is set to drain. We only have cohesion, which is increasing with depth for this thick layer of the material that we have. And also stiffness, these are defined in terms of undrained stiffness, Poisson's ratio close to 0.5. And these 2 are also increasing with depth. That would be case C. Then I have case B. So effective stiffness characteristic, and on top of that, we have undrained stress. The material also is going to be undrained behavior. So looking at the properties, you can see that, okay, strength is all defined, friction angle 0, cohesion, we have values, and stiffness, I'm just going to go to the previous slide, you can see the values are changing. So stiffness is changing, but the strength is going to be the same. So that's going to be my undrained B case. Drain A, all the material properties for the clay, these are defined in terms of effective stress and effective parameters. So stiffness is effective, and also you can see that we have friction angle for the materials. Cohesion is set to 0. Excuse me. So, and also the material is going to be undrained. Now, what we will see next is going to be the effect of different scenarios that we run for the undrained material on the results. For my reference, I'm comparing all these cases of undrained materials with a coupled bioanalysis, which I set the time steps to be short so that I'm actually mimicking undrained behavior. So you can see here on the right side, I'm showing you the distribution of pore water pressure in the system in the whole model at the final stage of excavation. the coupled analysis, and I actually have set these contour range to be exactly the same. So coupled analysis is giving me lots of suction developed in the excavation area. This undrained C is not giving me any of that because it's not considering that undrained effect at all. So you have gradual hydraulic pressure changing in the domain when you have undrained C material, and you don't see any of these suction in the undrained zone, in the excavation zone. In terms of displacement and support forces, you can see that, okay, the pattern and all that, they are matching perfectly, like not very perfectly, but the shape and all that, these are very similar. The values, the maximum values are different, but you're running different analysis anyway. Looking at undrained B, we are looking at excess pore water pressure. What is the change in the pore water pressure from the beginning at the final stage of excavation? You can see that the patterns are very similar between undrained B and A. So you have lots of suction in this area. This was the clay, that pink clay at the top, and this was the other greenish blue clay that we had at the bottom. You have all these generation of excess pore water pressure and suction developed in these two. So coupled analysis and undrained B, they are leading towards similar behavior. What I would like to mention as a side note is that, okay, you can see coupled analysis in this area and also undrained B in this area. This seems to have a little bit of issue with numerical stability because that's the coupled formulation. It's harder to solve those system of equation, and also we are doing that correction for the unsaturated case. This one is handling it better, looks like. Now, in terms of displacement, you can see again the same pattern and also support forces you see here. Let's go to the final. We are looking at undrained A. Again, very similar pattern for the excess pore water pressure here. And this time, actually, the displacement are actually closer values. They look very similar to the coupled analysis. I'm just using that coupled analysis as a reference to compare these three methods with it so that you see which one is actually generating better results in terms of prediction of excess pore water pressure and displacement. Now, comparing all these with the field observation. On the left, you see the wall deflection. On the right, you see the settlement behind the wall. And this is just the pattern for deformation of the domain. What I would like to point out here is the similarity that we have between coupled formulation and approach that we have for undrained A. In these two cases, because the basic formulation behind undrained A is very similar to Biot, and also the material properties are exactly the same. So these two are leading very, very close values, very close simulation results. The other two, they are a little bit different, but in this case, they are actually because of the material properties that we have in the model, they are predicting a more accurate result compared to the field. Now, this was all more Coulomb material. So you can take it one step higher and apply the same undrained analysis and all that for all these clay material, but simulate it with a more advanced constitutive model. So that hardening soil, for example, that we have, this is the same example. We have more layers of the material for clays because as you saw for the previous example, with the more Coulomb, we were using datum dependent properties. So properties were changing with depth. In this one, we have multiple layers so that we can actually mimic that with that hardening soil. All the properties of the hardening soil are defined in terms of effective stresses. You can see that here, friction angle and cohesion. And since these are clay materials, the question that was asked before, the dilation angles for these are all considered to be 0. The properties, again, coming from the reference that I have. And we can take a look at the results. RS2 results generated with RS2, and the Plaxis result that I have are coming from the reference that I gave you. We are looking at the wall deflection and also settlement behind the wall throughout all these steps that we have. And here is comparison of numerical results comparing to the field observation. So looking at more advanced constitutive models that are better calibrated to represent the field, you can have analysis results, numerical results that are much, much closer to what you see in the field. And the other point is that, okay, these two graphs, they are actually on top of each other. They are very close to each other. The last example that I have, this was an example that I presented when we had the webinar on North End constitutive model, and we were looking at undrained behavior of this North End material here. And what we were simulating was, okay, this new layer of tailing coming in, what will happen to the system and what is the effect of that initial state parameter that we have for the tailing material and North End constitutive model, and how is that going to affect the stability of this dam. So at the time, I showed you these graphs here for the loose case that we had for this material. When we were adding that top layer of new tailing coming in, we had generation of excess pore water pressure in the tailing material. We could predict it with North End constitutive model, and we predicted failure for this dam. And we ended up with this kind of graph here. So correlating between the state parameters and the failure and also displacement that we see at the crest of the dam. So in the denser cases, the dam was stable. When we were going toward looser material, looser state of initial state parameter for the North End material, we had the failure for the dam and it was not stable anymore. Now, this was one-shot material coming in. It was one stage of undrained analysis, and we ran the simulation like that. So it was initial stage and the embankment coming in. It was only 2 stages. We did not see the process of failure. What I'm going to present to you here, we will look at the process of failure, what is happening, and instead of only one shot, I will simulate it through multiple stages. So in this one, we are looking at the key aspect of this simulation. So the new layer of tailing that is deposited here is going to be deposited to during a certain period of time, and I have multiple stages to do that. The load that is coming from that new deposit is simulated by a stage load. So this distributor that I have at the top is simulated through 100 steps of step and stage. It's increased gradually going up. The boundary condition that I have for the tailing material and the water that is coming with it to increase the water level behind the dam is also transient. It is time dependent, head going up to the certain level that I was using in the other simulation. The material that I have here, it is going to be a North End constitutive model so that it can capture that static liquefaction. But the material is turning from drained to undrained, from the initial stage to the other stage that I have, second stage forward that the load is coming in, we will have undrained material. Now, to consider some transient groundwater analysis and dissipation of the excess pore water pressure during the time that this embankment, this new layer of tailing is being deposited, I'm running also a transient groundwater analysis. So the whole combination of these this setting that I have here, it is going to predict for me what is going to be the process to failure. Now, looking at one of these points that is actually on the path to failure, I can look at the effective stress path. This is a Q versus P prime, and starts from this point, and gradually when the load is increasing with time and all that, it is going back, and I have a sudden jump toward liquefaction. That is the gradual failure that I predicted with this set of scenario that all those components that I added to the simulation. And this last one is actually going to animate this process of failure. So at the top, you are looking at the development of excess pore water pressure during the stages that we have the embankment coming in. At the bottom, you see the progressive formation of shear band and the collapse of the dam. So at the top, you can see that, okay, excess pore water pressure increasing gradually, close to 90 at the moment here. This is nothing happening there. Still, there are some stuff, but gradually you can see that, okay, the shear band is also forming gradually. Close to 80% of the load that is applied, you can see that all of a sudden you have that shear band forming and you have instability in the dam. Okay. So the case that we made here, we combined all sorts of different kind of simulation that we had here. We had the solid analysis. It was time dependent. We had the transient analysis there as well. And we had also undrained material only for that northern material in this one. Now, if you have any further questions, Sina, do you have any more questions for me?
Yes. One of the questions that I can see it has been mentioned a few times is related to the permeability. So yes. They want to know how the permeability plays a role in your analysis. Or maybe if I rephrase it, when we are talking about undrained materials, does it mean that the water cannot flow outside of the material or no? For example, the water cannot leave or stays inside the pores of the soil.
Okay, so if I look at these simulation that I gave you for undrained footing, let's look at the hydraulic properties. I don't have any permeability for this one. So yeah. The assumption in this one is that, okay, nothing is moving, so there's no permeability needed for this one, that the permeability matrix and all that we need for this one is not needed. But in other cases, like for example, the simulation that I gave you for this tailing dam. So this one, we have the transient analysis on top of the undrained behavior. So even for this north end material, if I go to the second stage, you can see it's undrained, but there are hydraulic properties that can handle that transient phase. So we are combining both. I give you some time for the drainage, but again, when the load comes, it's gonna apply to the material as undrained. So it's a combination of these two happening together. So the permeability in this case is gonna affect the results to some extent, but in each stage that we are going, you have some time for the transient analysis based on the permeability and all that, so that you can have some dissipation of excess pore water pressure happening to it. But when the load comes from the next step, the effect of the load is going to be seen by the material as the material is undrained. I hope,
excellent. Thank you so much for clarifying it. Yeah, I can see the attending under the analysis very clear for them. The second question is regarding to the convergence. So when we have undrained material, we always face with some convergence problem.
Yes.
What do you recommend? What setting do you recommend us in RS2 to help us to get the convergence?
Okay. Let me open one of these. So this one is the one that is actually using advanced constitutive model and all that. This is hardening soil. Let me see what I actually use myself here. So in many cases that I'm dealing with some model that is having convergence issues. It could be from the complexity that we have in the formulation, coupled bioformulation, undrained material and all that. So that's gonna, okay, the whole system is complex in terms of convergency, finding the solution. It could be, okay, I'm using advanced constitutive models. Again, that is adding to the complexity of the system. I might have convergence issues. In those cases, what I will use that adaptive scheme that we have for the convergence. In this one, I can actually better control what portion of the load and all that I'm applying to the system. And what is my minimum load increment? So this is something that I'm actually mimicking what Flaxis uses when they are using hardening soil. So they have maximum 10,000 number of steps to run each stage. But I have here, again, minimum load 1E-4, so mimicking that 10,000 that they have. And also what this one gives me, the adaptive option, is that if any of these load increment that I apply to the system, if within that certain number of iteration, I did not get the convergency, the simulation is able to go back from the previous increment that we had the convergency and reduce the increment of the load. So it had the ability to recover from the past converged case, and it can continue by adjusting that load increment adaptively so that you can arrive to convergency. That would be my recommendation if I'm dealing with some simulation that I have issues with convergence.
Thank you so much. Next question is about the time step. How do you determine the time intervals in your coupled drain analysis?
Okay, so for that simulation that I had here, as you see here, I have some name in the name of the file. I have W2000. So for this simulation, based on the footing, based on all that, with the permeability of the material and all of that, you could control the rate of the load that could mimic the undrained condition. The value that I had, I don't have the calculation in the presentation, but if W that I was calculating, I can send the calculation to whoever asked this question. If W was more than 50, if I recall correctly, it would mimic the undrained condition. So for this one, I use 2000. So the rate, you can actually have some calculation for it so that you can mimic the undrained behavior for that. That could be problem specific.
For sure. And between all these methods that you were discussing today for undrained analysis, which one do you prefer and why?
Which one do I prefer? I'm coming from a background of bioformulation and all that, so I really appreciate the elegance of the formulation that we have for the UP formulation. That's in terms of mathematics behind it, I like that. The issue with that would be, okay, you might run into issues in terms of stability, convergence, and all that. So if I'm passing that, if I want to go for something simpler, I would use undrained material. And in terms of undrained material, my preference is A, if I have the properties of the material in terms of effective stresses, but that's usually not easy to have in many cases. Undrained B is the one that actually seems to be more practical to me, because that SU parameters is quite easy with you do vein test in the field and you can find SU very easily rather than taking material sample to lab and finding C prime and Phi prime. So undrained B to be easy and safe. If I want to use elegant formulation, I go coupled, but I have to have all those material properties.
Thank you so much for sharing your knowledge with us. The next question is regarding to SSR. Yes. Can we do SSR analysis when we have materials drained and undrained?
Yes. So actually, this is one of the poll questions that we will have later on in terms of stope stability. Yes, you can have SSR analysis for drained and undrained cases. We don't have it for advanced material model, like for example, that hardening soil, we don't have SSR for that. But for consolidation, drained, undrained, and all those scenarios that we have, if the material is one of those elasto-perfect plastic ones, like Morculum, Gerasupran, or those kind of material, you have the SSR option. Thank you very much. I appreciate you staying with us until to the end. This is the end for this webinar. We'll see you soon in another webinar.